Okay, now today's plan is this. Did we finish the lecture note number 5? Did we finish that part? We did not. Okay, one question about the class recording. Do you know where to find the class recording? Oh, you don't know how to find it? If you go to the Blackboard Collaborate, if you move the cursor to, there's a symbol. Oh, you know what? I will record a video, show you how to find it. All right, so let's not talk about it right now, because this way I have to change the screen and I will get everything. And I don't want to waste time for just to figure those out. Okay, so I will use the video to show you how to do it. Now, for today's lecture, I think it's most likely I will load it onto YouTube and break it into several sessions. I've been doing that for my another class, Dynamics, and it worked very well. So I think I can do that with good quality control. Now tonight we will finish force vibration. Of multi-degree of freedom system. Can you see my writing? Can you see it? Is that clear? Okay, you can understand. All right. And then we will talk about two different topics. One is called seismic design. I will talk about two different design codes. One is UBC 1985. The other one is IBC 2016. Well, IBC 2016 is similar to the ASCE 2016, so they are the same thing. ASCE, SEI 16. Let me put it here. So I have the space over there. I may have to re-raise the board as frequent as I can, because I really need a space. I really have to live with this tiny little whiteboard. And in the meantime, I have to live with the 3 glare spots. That's not very pleasant. The third topic I want to talk about tonight is the seismic risk analysis. Some of you may find the last topic useful for suppose your company is dealing with seismic risk problems or seismic risk related issues, and others working for like insurance company, they need to know if the company is designed and located in a seismic active zone, what will be the risk for this building upon the attack of a magnitude 7.5 earthquake? And what would be the likelihood for this building to collapse? With all these calculations in mind, you can come up with a reasonable number for the primary. Then you can use it to determine what will be the amount of like annual policy for seismic insurance purposes. So that will be today's plan. All right. And so let me erase this because I really need a space. Now, the lecture notes I updated last week. So you have the updated version, which this time I don't have to share the screen with you. And you have downloaded all my revised lecture notes, right?
Yeah.
Okay, so you have, I finished lecture note number 4, right? And I think did I finish number 4?
Yeah.
Last week. I think I did. Lecture note number 5. You can download it from the class table. Okay. Now, so how do we solve the problem? How do we solve the force vibration of multi-degree of freedom system? First of all, for single degree of freedom system, you know that you're dealing with a single mass and single acceleration denoted as U double dot plus C damping coefficient times U dot velocity plus K times U stiffness coefficient times displacement. And this equals to two possible results. One corresponds to homogeneous solution. Okay. Some people are still logging in, logging out, and to some point, I will not be able to accept or admit more students because I will be standing away from my computer. Okay, so you want to make sure that's why I spend a little more time at the beginning to make sure there's no technical difficulties. One possible result is when this carbon equation becomes 0, as we know that corresponds to homogeneous solution, and the other one corresponds to a function of P of 0. This corresponds to the particular solution, as we know. So when this becomes 0, this is U of sub H, homogeneous solution. We already know that when it's not 0, it becomes some sort of function, and that corresponds to a particular solution, U of T. What is the total solution? The total solution, or the general solution, is what we call U of T. Now this one, of course, equals to a homogeneous solution plus the particular solution, like this. That you already know, right? Okay. And this is the case for single degree of freedom system. For multi-degree of freedom system, we no longer have just single values, as we already know. You have to deal with S matrix times acceleration vector plus damping matrix times the velocity vector plus stiffness matrix times displacement vector equals to, of course, there are two possibilities. One is still 0. That means that's the free vibration of multi-degree of freedom system. 0, of course, is not just 0, but it's 0 vector. Or it is equals to a force vector. Now the force vector is a function of time. The same idea. When this carbon equation becomes a 0 vector, that means this corresponds to a homogeneous solution, and it is not, that corresponds to a particular solution. Combining these two leads to the general solution, which is this. But the idea is pretty much the same, except when we determined the displacement vector here, we said that the displacement vector is and can be written by linear summation. Of two different components, right? And that's the summation from I equals 1 to degrees of freedom, which is denoted by regular n here. So what are the two components we have? What is the first one? Anybody remembers?
Shape function.
Shape function. Shape function.
Yeah.
The first one is called shape function. What do we call it? We call it phi, right? So we have phi sub I, and shape function only a function of space. So it's a b of I of x. Of course, you know that this has to be a vector. Times what?
Z of t.
Was z a generalized coordinate? And this is also the I of t. Once again, first one is about space, and the other one, z, is about time. We have these two.